Take a look at 3 practice questions. Actually, we're going to do 2 of the practice questions on page 107. Projectile motion questions. Starting with number 2, it says an arrow is fired horizontally with a speed of 25 meters per second off the top of a 150-meter high cliff. So this is the height of the cliff right here. The arrow is fired with a velocity of 25 meters per second. We know the shape of that path looks like this. It's a parabola or a half a parabola. We want to find out how far it drops in 2.5 seconds. So a little bit different than the example questions we did. We're given the time. We want to find out how far it drops. Now, don't misinterpret what's happening here. Okay, this is how far it drops. This distance right here is what we're looking for. Understand in this question, this 150 meters is 100% completely, what word? What's the word I want to say? 100%, it is completely irrelevant. Think about that. The height of the cliff is 150 meters. Does it say that the arrow falls all the way down? No. It says how far does the arrow fall? Maybe the arrow falls 3 meters. Maybe it falls 149 meters. It doesn't matter how high the cliff is. The height of the cliff doesn't determine how far the arrow falls. Maybe the cliff is 1,000 meters high. The arrow is still going to fall the same distance in that time, right? The height of the cliff doesn't affect how far the arrow falls. Sometimes we're given numbers that just don't matter. Like in this case, the height of the cliff. Okay, if I was to ask Josh, what color is my car? Or sorry, if I was to ask Josh, how fast is my car moving? And Josh said, your car is blue. Josh is correct, right? My car is blue. He didn't answer the question. And he gave me a piece of irrelevant data, right? It's completely irrelevant. It's correct, but it's completely irrelevant. The color of my car does not affect the speed of my car any more than the height of this cliff affects the distance that this arrow falls. Does that kind of make some sense? It doesn't matter how high it is. What matters is how long it falls for. That's what determines how far it falls. Okay, so we're going to do our thing here. We're going to say x and y components. What equation do we use to describe the x component today and on Thursday's test? Speed is displacement over time, or velocity is displacement over time, because horizontally, the velocity doesn't change. Horizontally, it remains 25 meters per second the whole time. Vertically, it speeds up, but not horizontally. Okay, the vertical component, I'm going to use which equation to describe? Better get it, because you got to do this on Thursday. Yeah. VIT plus 1 half AT squared. Really, that's the equation for a parabola, right? Those of you who have done parabolas, okay, if you think you might forget which equation to use, which of the acceleration equations, then think back to that equation for a parabola. Y is equal to ax squared plus bx plus c. That one's the one that looks a lot like it, right? So that's your reminder that this is the one that we use. Let's start subbing numbers in. Do we know the horizontal velocity? We sure do. It's 25 meters per second. Do we know the horizontal displacement? Nope. Do we know the time that it's in the air for? Yep. So we solve for delta D here, and it works out to be 62.5 meters. Now, what does that 62.5 meters represent? Yep. Yeah, it's the x displacement. It's this right here. Is that what I'm looking for? Nope. So I just solved for something that wasn't what I'm looking for. Is that okay? Is it wrong? When Josh told me my car is blue, is that wrong? No. But if I asked Josh how fast was my car moving, and he can tell me my car is blue all he wants, that's fine. He just has to keep going. He hasn't done anything wrong. He just has to keep going to get the answer that I'm looking for. That's what we got to do here. So we go to the y component. What's the y displacement? 150? No. We can't just randomly write down a number for anything, right? If the arrow doesn't fall 150, that's not the displacement. We don't know what the displacement is. In fact, that's what we're trying to find, right? The vertical displacement. What's VI for the y component here? How much of that 25 meters per second is up and down? 0. So let's say 0 times time is 0, okay, plus 1/2 of neg 9.81 times, well, this time we have the time, 2.5 squared. Let's figure this out now. Okay, on our calculators, let's say 0.5 times negative 9.81 times 2.5 squared. That gives us a value of 30.7. It's actually negative 30.7 meters. There's my answer. How far did this thing fall? 30 meters. Okay, the cliff was 150 meters high. It fell 30 meters. What if the cliff was 200 meters high? How far would the arrow have fallen? 30 meters. What if the arrow was 5,000 meters high, or the cliff was 5,000 meters high? How far would the arrow have fallen? 30 meters. Okay, do you see how the height of the cliff is not relevant here? It's not important? Okay, let's take a look at number 3. 3 says, what's the horizontal speed of an object if it lands 40 meters away from the base of a cliff? Draw the picture. Draw the picture here. Here's the height of the cliff, 100 meters. And this time, this object lands 40 meters away. We want to find the horizontal velocity there. Make sense? X and Y. Always use the same equations here. V is equal to d over t for x. And y, we say d is equal to VIT plus 1/2 AT squared. V is, do we know what V is? Nope, that's what we're trying to find, isn't it? Do we know what delta D is for the x component? 40 meters, right? Yeah, it's 40. It says the object lands 40 meters away from the base of the cliff, so the horizontal displacement is 40 meters. We don't know what the time is. That's okay. Move on to the y component. Do we know what the vertical displacement is? Negative 100 meters. So why is it that last time we could not use the 150, but this time we can use the height of the cliff? Yep. Yeah. In question 2, it does not say the arrow goes all the way down to the base. In question 3, it does. It says it lands. So we know that the vertical displacement here is negative 100. VI for the y component is 0. It's launched horizontally here. 0 times time is 0 equals 1/2 of negative 9.81 times t squared. I'm going to simplify this a little bit. Half times neg 9.81 is neg 4.905. Take that over by dividing. Oh, we end up getting the same time as we did in another question we did. I get a time here of 4.51524 seconds. 100 divided by 4.905, then square root that. Now let's take that and put it up here. We end up getting 8.86. And sure enough, that's the answer that's in the book there. Here's a question that I want you to work on at your desks. We launch a ball at 10 meters per second horizontally off the edge of a cliff. We don't know how high the cliff is. That's okay. It lands 30 meters from the edge of the cliff. Let's calculate how high the cliff is. Let's calculate this number right here. Remember, you always got to start the same way, right? I'll get you started. X and Y. Remember the equation that we always use for X? The equation that we always use for Y? Sub some numbers in. See what you get. Okay, something's going to pop out of this, and eventually it's going to be what you're looking for. See what you can do. So what equations do I use here? Well, for the x component, thank you. For the x component, it's always the same one, right? Always. No exceptions. Zero exceptions. For the x component, it will be v is equal to delta d over delta t, or group A equation, because horizontally, the velocity of this doesn't change. If it's 10 meters per second horizontally here, it's 10 meters per second horizontally here, and here, and here. The horizontal velocity does not change. So we have to use v equals d over t. But vertically, we use an acceleration equation, a group B equation. I'm going to try if d is equal to vit plus 1/2 at squared. And the reason that we're going to try this equation is because that vertically there's acceleration. The vertical velocity up here is 0. The vertical velocity here is a little bit higher. And then it's even higher. And then it's even higher. Horizontally, it's constant velocity. Vertically, it speeds up. So we have to use that group B equation. Let's start subbing numbers in and see what happens. Do we know the horizontal velocity here? Christine, do we know the horizontal velocity? 10 meters per second. Good. Excellent. Do we know the horizontal displacement? Somebody else. Tim, I was going to call you Josh there. Tim, what's the horizontal displacement? It's 30 meters. Good. And we solve for time there. Notice in these ones I tend not to rearrange first. I tend to put the numbers in and then rearrange. Okay, I want to take the t up to the top. And then the 10 goes down, so it becomes 30 over 10, or 3.0 seconds. Is that what I'm looking for? No. Is that helpful? Maybe. In fact, I think it probably is going to be helpful. If it's not, oh well. Okay, let's go to my y component since I haven't found what I'm looking for. Delta d, I don't know. Do we know what vi is? Josh, do we know what vi is here for the y component? How much of that 10 meters per second right here is up and down? Right. Good. So 0 times time is 0. So d is equal to 1/2 of negative 9.81 t squared. Oh, we found the time, didn't we? It was 3.0 seconds. So let's do this on our calculators now. Let's say 0.5. 0.5 of times 9.81, negative 9.81, times 3 squared gives me negative 44 meters. Now, there was a couple of people that asked me a question about the negative. Is it okay to have a negative height? Well, really, the height of this cliff is 44, isn't it? The ball fell 44, so the displacement is negative 44. The height is actually positive 44. But we're not going to lose any sleep over that, right? Negative, positive, whatever. We're going to mark that right either way. Okay, how many people got negative 44 meters? Good, good. Okay, I want to do another example here that's going to look a little bit different. It's still real similar, but a little bit different. What we're going to do is combine a couple of things that we've done so far, namely the projectile motion questions, along with a little bit of vector analysis. Okay, the example we'll do in just a second, but I want to kind of set it up here first. Let's say that we're not kicking a soccer ball off the edge of the building horizontally, but rather we're kicking a football up at an angle of, let's say, 30 degrees at a speed of 10 meters per second. What happens to that football? Follows a parabola, right? Now, we know that we're going to have to do this x and y component thing. And we know that we're going to have to use for x, v is equal to d over t. Always. For projectile motion, it's always the same. It always starts the same way. But there's something else that I should do here before I go any further. I may have even, maybe even should think of it before this. What do you see up there that kind of jumps out at you a little bit? Sorry? Good. We got a funny angle. Okay, and what do you say when you see a 30-degree angle? I don't like funny angles. So what do we do when we don't like funny angles? What do we do? Demi, what do we do when we don't like funny angles? Yes. We get rid of it, right? We take it off to the side and we get rid of it. So let's do that. Here's my 30 degrees. Here's my 10 meters per second. Let's make this x, and let's make this y. We're going to say cosine 30 degrees is equal to adjacent over hypotenuse. X is 8.66. And we'll say sine 30 degrees is equal to opposite over hypotenuse. Y is equal to 5.0 meters per second. And then we block it off, no different than when we were doing those vector addition problems. And then if I want, I can draw them in over here. 8.66 and 5.0. So instead of having the 10 meters per second, I now have 8.66 straight over and 5.0 straight up. Now, let's start subbing numbers into these equations. What's the horizontal velocity here? Yep, 8.66. It's not 10 meters per second, it's 8.66. What's the horizontal displacement? How far does it go? We don't know, do we? We don't know. That's probably what we're trying to find, to be honest. We don't know how long it's in the air for either, though. Is that helpful to me? Not yet, anyways. Maybe it never will be, I don't know, but it's certainly not helpful to me yet. That's okay. If we didn't get what we're looking for, what do we do? Keep trying. Sorry, what was that? Move on. Yeah, move on. Good. Oh, here's one for you. What's the vertical displacement here? Good, Demi. The vertical displacement is 0. How come? Why is it 0? Yeah, it starts on the ground and it ends on the ground. So although it goes up into the air, it ends up at the same height that it started, the same vertical position that it started. That's important. Okay, that's critical to this. Okay, those last questions that we did, the vertical displacement was negative something. In these ones, the vertical displacement will be 0. Okay, what's VI for the y component here? Sean, what's VI for the y component? 5, good. Okay, it's not 10. We replaced the 10 with 8.66 and 5. And somebody already told me, who was it? Somebody told me that the 8.66 went here. Who was that? Okay. The y component is 5.0 meters per second. Now, we don't know what the time is. A is neg 9.81. Now, that looks pretty tough to solve for t, doesn't it? We'll simplify it a little bit, although it's still going to be tricky to solve for t. We're going to say 0 is equal to 5.0 t, subtract 4.905 t squared. Where did that come from, the negative 4.905? Yeah, it's a half times negative 9.81. Now, you guys might remember from math class that I can do whatever I want to this equation as long as I do it to every term. I can divide or multiply every term by 28,112 if I want to, or I can divide every term by t if I want to, as long as I do it to every term. Does that make sense? So do you remember that rule in math? You're allowed to do whatever you want as long as you do it to every term. What's 0 divided by t, Josh? 0. What's, somebody else? 5t divided by t. 5. What's 4.905 t squared divided by t? Rachel? That's the toughest one here, isn't it? Anybody? Anybody? It's just t. One of the t's on the top cancels with the t on the bottom. There we go. Now it's looking a lot better, right? divide every term by t, and now I've got this equation, 0 is equal to 5 minus 4.905 times t. I'm going to take the 5 over by subtracting. Negative 5 is equal to negative 4.905 t. And now let's divide by negative 4.905, because it's multiplied by t. Five divided by 4.905 gives me 1.0194. There's how long this ball was in the air for. Now sub that into here. We take the 1.01 up by multiplying, multiply it by 8.66, and I get a horizontal displacement of 8.8 meters. How far does this football travel? 8.8 meters. So next time you're playing football, let's say you're, not high school football, you're well beyond high school football. Let's say playing like NCAA Div 1 football, you're a field goal kicker. That's what you are. You're a field goal kicker. And you're like, hey, coach, I can do this. Okay, I learned how to do this in physics class. Okay, here's what I want you to do. I want you to take out your protractor and your calculator, and I want you to show the coach and calculate how fast you need to do it in order to kick the field goal. Kind of working backwards. Calculate how fast instead of how far, right? Okay? You can do it. You can make that 50-yard field goal, okay, if you just know some physics. And maybe you don't want to try that, I don't know. Guys, does that make sense? What's different about this question versus this question? There's three things that are different about it. And they're all colored here. This is different. Remember in the last question, the horizontal velocity was just the number that was given to me, 10 meters per second. This time, I have to find a component of it. The initial vertical velocity is different. It was 0 in this question. It's the vertical component of the initial velocity in this question. So we have to do some trig to find that. And finally, this is different as well. It's 0 now, the vertical displacement. It was negative something. Negative, in this case, we found negative 44 meters. Right? Those are the only three things that are different. You recognize that? Just sub in your numbers and solve just like you did in those questions you had for homework. Let's take a look at page 109, and I'm going to ask you right now at least just to do, no, that's not the one. That's the wrong one. Instead of doing those practice problems, we haven't done this example yet. Do this example. Okay, do this example right now as your practice question, and then we'll take a look at that after you've had a chance to do that example. All right, question says, ball was launched at 22 meters per second, angle of 30 degrees. We got a funny angle here. We got to take it off to the side and get rid of it here. So let's do that now. 22 meters per second, an angle of 30 degrees. I'm going to draw a triangle around that, as I do always. Let's label this X, label this Y. Let's say that the X component can be, it's the adjacent side of the triangle, right? So let's say, ladies, that the X side can be found by cosine. Cosine 30 degrees is equal to X over 22. And sine 30 degrees is equal to opposite over 22. This is 11 meters per second. I'm not sure what 22 cosine 30 is. Anybody have that? 19.05, thank you. So let's box this off now. Okay, let's box this off. And now let's do our thing with X's and Y's. For the X component, we always say what, Rachel? Which equation do we use for X? Yep, absolutely. V equals delta d over delta t. For the y component, we always say d is equal to VIT plus 1/2 AT squared. We start subbing numbers in here. Do we know the horizontal velocity? Francis, do we know the horizontal velocity here? V here for x? Yeah, not 22, no. 19.05, right. We want the x component of that 22. Remember that the 22 is gone. It's dead to us now, right? We've done our thing with the 20 meters per second. We never want to do that again. Delta D, we don't know. We don't know what that is, so we'll just... Delta T, we don't know that one either. All right, that's fine. Let's go over here to the y component. Delta D for the y component is... other Rachel, what's delta D for the y component? 0, good. VI, because it ends up on ground level, well, it ends up at the same height that it started at. What's VI for the y component? Jared, what's VI? 11 meters per second, good. Delta T, we don't know. Negative 9.81 here for A, T squared. Let's divide everything by T. We end up with 0 is equal to 11, subtract 4.905 T. 11 goes over by subtracting. And then we take the negative 4.905 over by dividing. Get a time here of 2.24 seconds. That's my answer, isn't it? Done. So did I need to do the x component? No, I didn't. I didn't know that when I started. That's okay. So I did a little bit of work that I didn't need to do. Hey, if you were looking for the horizontal displacement, how far this ball went, then you would take that time, sub it back into here, and solve for delta D. We just weren't asked to find that. I got one question that I want you to work on tonight for homework, okay? We're going to launch a soccer ball at 20 meters per second at an angle of 30 degrees. I want you to tell me tomorrow, with work, how far that ball goes. Okay, that's your question for tomorrow.